It is now 12 o'clock here in California, so let's begin. Good morning, good afternoon, and good evening, everyone, and thank you for joining in today's webinar. My name is Paul Nishihira, Applications Engineer with GoEngineer and located here in Northern California. A couple of noteworthy items before we begin. The entire audience will be muted for the duration of this webinar. This webinar is being recorded and will be made available for everyone to view later on our GoEngineer YouTube channel. And feel free to contact me should you have any questions after the webinar is finished. I have a large amount of information to share with everyone and want to be cognizant of your time for today. Thank you in advance for your understanding. Prior to GoEngineer, my past job experiences involved working in a traditional engineering department as a mechanical drafter and designer, at manufacturing facilities, machining and CNC programming, and even at remote locations that shall not be named as an aircraft mechanic. Despite all these different environments, they all had one thing in common, and that was to work smarter, which will save you time. And that is what today's webinar is all about. It's all about working smarter and saving time using CAMWorks 2020. One item of note, starting in 2018, SolidWorks partnered with CAMWorks and released a fully integrated manufacturing solution package as an entry point into the world of CNC programming. Known as SolidWorks CAM, it is available when using a license of SolidWorks Standard, Professional, and/or Premium with active subscription from your reseller. Most of these time-saving features are available to the users of SolidWorks CAM. If you would like more information on this or any other items, feel free to contact me after this webinar, as I will be more than happy to answer any questions. Now, who would have thought that having a properly designed SolidWorks model will help us save time in CAMWorks? Well, let's take a look at a few of the following items. Number 1, the explicit use of a SolidWorks coordinate system. Properly defining your CAMWorks machine environment by utilizing a SolidWorks coordinate system can be the best thing since sliced bread, or the most frustrating experience using CAMWorks, as your simulate toolpath is displayed incorrectly, CNC code output is reversed, or worse yet, nothing graphically generates at all. This important SolidWorks feature refers to the home point or main zero position of your machining center. Simply put, it establishes how your model is virtually positioned on the machine table bed and relative to the machine spindle. Not only does it define the default G-code origin, it also defines the X, Y, and Z machining direction and acts as a reference point if subroutines are used. So, save yourself time and frustration by using a SolidWorks coordinate system before you do anything else. It's also mandatory for assembly machining, mill turn, and higher levels of positional and simultaneous 4 and 5 axis, as it establishes rotary and tilt axis indexing. Number 2, for hole operations, use Hole Wizard to save time. The key benefit of using SolidWorks Hole Wizard is CAMWorks can leverage that feature along with its parametric information to streamline the assigned strategy and generate your toolpath operations with just a few mouse clicks. In this example, after running extract machinable features, CAMWorks is assigning a specific quarter 20 thread strategy based upon this SolidWorks Hole Wizard feature. After a few mouse clicks of generating my operation plan, then generating toolpath, you can see how fast and easy CAMWorks is able to establish the machine order and utilize the correct tools to machine that SolidWorks Hole Wizard feature. As comparison to this existing SolidWorks cut extrude, you can see that it created a regular drill strategy based upon the hole diameter. If I wanted to be specific, let's say a 3/8 16 tapped hole, I would need to access the hole parameters dialog, strategy description, method type, then the library of tools database. After all of that, I would still need to generate my operation plan, then generate toolpath, and verify that I'm using the correct tools for that SolidWorks cut extrude. Lots of mouse clicking, don't you think? Number 3. Assign colors to model faces for use in CAMWorks. Think of this technique as establishing selection sets inside of SolidWorks, but for ease of use in CAMWorks. What I would like to do is create a 3-axis undercut toolpath using only these chamfered surfaces. Right mouse button click on a given face, select tangency, then choose a color that is meaningful to you when we change over to the CAMWorks environment. Number 4. Utilize 3D Sketch and Repair Sketch for boundary edge selection. This technique is related to item number 3 since I'm using the 3-axis undercut strategy. What I want to do next is create and use in CAMWorks a given 3D sketch, rather than wasting time individually selecting model edges to establish my boundary conditions. With an active 3D sketch open, simply right mouse click on a given edge, select tangency, then utilize my sketch tools to convert entities. Now, since I don't want to be bothered by broken or overlapping sketch geometry, a few mouse clicks of running Sketch Repair with its default settings will highlight and/or address this. This time-saving technique is really helpful when used on imported CAD models such as Parasolids, STEP, and IGES formats. Number 5. 3-axis undercut. I did put an asterisk next to this as I think of this feature as a cool bonus item. When generating toolpath for organic shapes and surfaces, CAMWorks offers many choices which addresses the challenges the CNC programmer encounters. Strategies such as area clearance, constant step over, and pencil mill are some examples used to meet the demands of aerospace, medical, consumer use tooling, and product needs. What if we need more capabilities to meet the requirements of complex shapes, surfaces, or perhaps even undercuts? This is where CAMWorks MultiAxis Machining 3-axis undercut will help meet these requirements and save us time. The multi-axis machining engine is different from the previously mentioned multi-surface strategies. It offers you more control of the cutting tool and how it interacts with the model geometry. Although with this example, I'll show you a more traditional 3-axis approach, multi-axis machining is a great application for 4 and 5-axis simultaneous programming. Building on what I had talked about in items 4 and 5, what I want to do next is only machine this chamfered feature using a multi-axis machining strategy. I'll save time by using the feature type, faces by color, to select the surfaces I only want to machine. The strategy that I want is 3-axis undercut, and you can see that it's defined in the TechDB to use a 1/4-inch diameter lollipop cutter. And we'll select the green checkmark to make things official. After generating operation plan, I'm going to be specific on what I would like to control in the operation parameters dialog. This is where I strongly recommend that you work methodically as there are many options available to us on how we can create the most efficient toolpath for the geometry selected. First, establish what kind of tool we are using. In this case, I'm going to be using this 1/4-inch diameter lollipop cutter. Next, establish the pattern type needed. Offset from curve will be the best choice as I can specify the curve needed to offset from. Remember that 3D sketch that I had previously created? Well, it's right here and available to me with a simple mouse click And the key here is to save time by minimizing any excessive or unnecessary mouse selections. To finish the values on this tab, I'll make a few adjustments to the direction of cut and establish my edge margin values for a clean looking toolpath. For my axis control, we will be using our traditional 3-axis. However, we do have the capabilities for 4 and 5 axis as well. I don't have any special requirements for entry and retract other than making sure my lollipop cutter returns to the specified clearance plane of 1 inch of my Z-plane. Changes to the finish requirements are minimal with the exception that I don't want to have any adaptive cuts and I don't want to have any extend or trim functions. Just a simple 3-axis undercut toolpath that machines this chamfer feature only. Adjustment to values on the links tab will be changing my default percentage values to a specific number. For links along cut and links between cuts, I have no requirements needed for entry-exit methods. Now, all these tabs may seem a little overwhelming at first, and this is why we at GoEngineer teach recommended workflows for multi-axis machining. Once I select Preview to update these settings, the reward, as displayed here, is a very clean, simple, and efficient toolpath which leverages only the colored surfaces and that it is bounded by the 3D sketch which I had previously created in SolidWorks. 3-axis undercut is a great time-saving technique versus traditional selection of all surfaces, then using a series of contain and avoid areas to obtain the desired toolpath needed. If you want a deeper dive look at this technique, type in 3-axis undercut in the search field of our GoEngineer YouTube page. It's well worth checking out. Now, let's move on to the meat and potatoes of which is titled CAMWorks. These featured items range from alternative techniques to what's new for 2020 and even alternative options which will help program efficiently and save time. Number 5, using CAMWorks Helix Spiral Technique. Whenever faced with machining challenges, quote unquote, CNC programmers and machinists always seem to find solutions to get the job done. With that mindset, CAMWorks offers you the flexibility to easily generate helix spiral entries for circular holes and pockets to save time. By minimizing the use of multiple cutting tools, or if you have a machining center that does not have an automatic tool changer, this time savings workflow is for you. If you recall earlier, this diameter 3/4 inch by 1/2 inch deep SolidWorks cut extrude is represented as a hole 1 feature after running CAMWorks extract machinable features. What I'm going to do next is create a contour milling operation using this CAMWorks feature and only using a 3/8 inch diameter center cutting flat end mill. After selecting the green check mark, I am now inside the active operation parameters dialog of the CAMWorks operation tree. Again, I'm going to verify the tool size and type graphically as well as by its settings. Switch over to the Contour tab to adjust the cutting depth by the percentage of the diameter of the tool. And finally, on the Feature Options tab, adjust my entry type to spiral. The formula that I find useful is based upon radius. If the hole diameter is 3/4 of an inch, the radius will be 0.375 minus 0.1975, which is the radius of the tool plus 10 thousandths for final cleanup at full depth of cut. After selecting Tab, CAMWorks will calculate the required value of 0.1775 automatically. Next, I'll select Preview to update the Operation Parameters dialog. Then Toolpath Simulate to graphically verify that the toolpath is spiraling upon entry, then completing its final pass at full depth of cut. So, what I've just shown is an alternate way of only using one tool which replaces the workflow of 2 or 3 tools such as center drill, drill, and a ream to save time by minimizing tool changes, or if your machining center does not have an automatic tool changer. Number 6. Probe operation. New for CAMWorks and SolidWorks CAM 2020 is the ability to generate probe operations. Using a supported post-processor that is compatible with your machining center, this functionality will save time by allowing you to program important CAMWorks features to help generate critical data such as tool length offsets and work coordinates of your model. Another time savings benefit is utilizing your machining center as an in-process inspector by minimizing or eliminating unnecessary teardown and setup of your part. Using the previously machined CAMWorks Hole 1 feature, I'm going to show you how easy it is by generating a probe operation from the command manager. I'm happy with the default tool selection, and on the Feed Speed tab, I can verify the feed rates as well as the protected rapid travel rate values. Selecting the Probe tab will give me options of what I want to probe. X, Y, Z, and even specific probe cycles are available to me. For this example, I want to use a bore cycle, and by selecting the cylindrical feature, CAMWorks will graphically show me how the probe tool will pick up the center of this bore. By selecting Update Work Coordinate System Offset, I can tell CAMWorks to update my work coordinate to G55. Now, let's make it official by selecting Preview and then step through Toolpath to graphically see how easy it is to view the probe operation. So, for those of you who've been waiting for probe functionality in CAMWorks and SolidWorks CAM, I would highly recommend checking out this new time savings feature for 2020. Number 7. 2.5 axis volume mill versus traditional roughing. High-speed machining, high-volume machining, high-efficiency machining. You probably have heard of these fancy terms at one time or another, and what it basically means is removing the maximum amount of material quickly while maximizing tool usage and lifespan. CAMWorks and SolidWorks CAM offers this time savings, fully integrated feature called Volume Mill by Accelerative Technologies. In this example, I have already created my SolidWorks coordinate system, defined the machine environment, and generated roughing operations. So we are able to see the differences between these two techniques. Inside the operation parameters of Rough Mill 1, I'm going to be using a 1/2-inch flat end mill as my tool of choice. Different pocketing pattern types such as pocket in, zigzag, and plunge rough gives us multiple ways of removing material from this pocketed area. Let's use the pocket out pattern with spiral helix entry and default settings and see what we initially have. One item of note, because of the given toolpath travel and sharp directional transitions, we're going to be somewhat limited to how deep we can cut and how much step over is possible. Shock loading of the tool or interrupted cuts, cutting tool chatter, and even machine chips binding up in this pocket area are items to consider, especially if you don't have an adequate supply of chip evacuation available. All this are factors in saving time. If we look at the Optimize tab, we can see an estimated machine time of 2.6 minutes, under ideal conditions, of course, for just this one pocket. For comparison, let's take a closer look at this next rough mill operation. The SolidWorks feature is still the same as the other feature, the only difference is that I'm using volume mill. Inside of this operation parameters dialog, I'm still using the same 1/2-inch diameter flat end mill. On the roughing tab, I'm going to utilize the volume mill pattern. Located just to the right of this selection are 3 dots. Once expanded, this gives me access to specific volume mill settings for this operation. Additionally, on the Feed Speed tab, when I select Define By Operation, The volume mill technology expert is available in which I can influence the overall spindle speed and various feed rates for this operation. Material being machined, coating of the cutting tool, and tool holder type are just some of the many settings available for control. At the very bottom, you even have this nifty slider bar to drag how conservative or aggressive you want to be when machining this feature. It really doesn't get any easier than that. If you're curious on what type of tool Volume Mill offers, I'll select Preview to update its current settings, and as you can see, we now have one spiral helix entry at full depth of cut, trochoidal type milling, which is a fancy way of machining a slot wider than the cutting tool's diameter. Not only does this effectively engage the flute length of the tool, it minimizes shock loading and thereby extending tool life. Now, when we switch over to the Optimize tab, you can see that we have an estimated machine time of 1.1 minutes, which is a significant amount of time savings for this part. And as a bonus, we are also saving money by extending tool life as well. Number 8. 3-axis volume mill and CAMWorks adaptive roughing. For individuals who are needing to rough out material at the 3-axis multi-surface level, CAMWorks offers this time savings, fully integrated feature as well. In this example, I have already created my SolidWorks coordinate system, defined the machine environment, and generated an area clearance roughing operation for this mold cavity. When I switch over to the operation tree, I have several toolpath examples generated, so we can see the differences between all techniques. For this first example, I'm using a 3/4 inch flat end mill along with my traditional pocket out pattern type. As noted on the screen, using optimal feed and speed, depth of cut, and step over, I have an estimated machining time of 166 minutes, which is way too long for this type of cutting tool. In this next example, I'll be using volume mill as the pattern type. All volume mill controls that are available at the 2.5 axis level are also available at the 3 axis level, along with optimized trochoidal movements, which maximizes material removal rate while extending tool life. In this last example, CAMWorks offers their own version of high efficiency machining called adaptive roughing. This is an alternative to volume mill with traditional controls such as feed and speed, depth of cut, and step over as indicated by the volume mill technology expert being grayed out or not available. As shown in the display, this roughing operation will give you unique toolpath, and controllability is not as extensive as volume mill, but is a time savings alternative to traditional pattern type roughing such as pocket in, pocket out, etc. The CAMWorks Technology Database, or TechDB, is the brains behind CAMWorks. Not only does it offer you powerful, out-of-the-box functionality, more importantly, it enables you to customize and incorporate the best practices that meets your needs of programming efficiently and ultimately save time. Number 9. Combining strategies and exploring independent controls locally. In this example, I have already created a SolidWorks coordinate system which is going to represent the top surface and dead center of the part. Next, I'll go through the workflow of establishing my machining environment by selecting the appropriate type machine, tool crib, post processor, and assign my fixture coordinate system by using the existing SolidWorks coordinate system. Next, I'll define my stock by using an existing sketch to determine its profile, then select the top face to establish my overall thickness. To determine what type of machinable features are available, I'll run extract machinable features and pick and choose what I want when generating my toolpaths. Let's explore this irregular slot 1 strategy as I want to change it to a rough finish edge break. Once I select the green check mark, I now have this specific strategy assigned, and I'll generate my operation plan, then generate toolpath to see what I initially have. Now, let's see if I can make this rough mill 1 operation more efficient. First off, I'll change it from offset roughing to volume mill, then select preview to update. Since I'm content with this operation, I would like to apply it to these other irregular slot types. All I need to do is right mouse button click on this rough mill 1 operation, combine operations, and using the features list, populate my additional irregular slot features to combine. As best practice, I'll generate my toolpath once more to actively see all settings now applied to other features. Let's do another example using this contour mill 1 and explore some independent controls. On the contour tab of the operation parameters, I'll verify a few settings and make sure this is what I need. Then over on the lead in tab, I'll make some adjustments so that I have the proper lead in and lead out off the part. Once I'm content with the overall settings, I'll go through the same process of combining as I had done previously with the rough mill 1 operation. Select OK. Aha! You're going to notice that I don't have the desired toolpath for these other features. Not a problem. If we access the Operation Parameters dialog and then the Lead In tab, in the Features drop-down menu, you can see all of the irregular slot features. Now, since I want to apply the settings of irregular slot 1 to all features, it's simply a matter of checking this box. Select Preview for Update, and you now have all lead in and lead out applied to everything. So here's a fun fact. Anywhere that shows a paintbrush icon or apply to all will, well, apply the current settings to all features. And here's something cool. If I want to independently control the entry type of irregular slot 2 to something different, let's say spiral entry, make sure this feature is currently active and simply change whatever settings that's needed and it will only apply it to that specific feature. Pretty cool. As good measure, I'll repeat the workflow for this edge break as well. By combining operations, you can efficiently program one operation, then apply it to other like type features, or have them independently controlled if desired. Again, the key here is to work efficiently, which ultimately saves time. Number 10, map mill features globally. In keeping with the same idea of working efficiently, I want to create a customized strategy of roughing out this pocket, then contour finish the perimeter to its final size, and finally edge break or chamfer the upper perimeter edges. Sounds easy, right? Well, how about we apply that same strategy to this open style irregular slot? Say what? That's crazy. Well, I'm here to show you how by explaining how the TechDB works. Accessing the TechDB is done within an active session of SolidWorks or independently by the Windows Program Manager. Inside Mill, Features and Operations, we have access to all the different CAMWorks feature types. Although the nomenclature is different from SolidWorks, it really means the same as a boss extrude, cut extrude, hole, etc. What makes it unique to the CAMWorks TechDB are the predefined strategies, the operations, the conditions, and the assigned cutting tools. Keep in mind that all of these parameters are customizable to suit your needs and company's best practices. Now, if we dig a little deeper and within Map Mill features, we see over on the left side our CAMWorks original feature nomenclature, and on the right side, the Map to Feature drop-down menu to which we can associate to the original feature. For some companies, a pocket is a pocket and a slot is a slot, regardless of what the profile shape is. What this means to you is that you can simplify many of these feature types to specific strategies, rather than try to manage each individual original feature. Although this doesn't apply to everybody, it's a great way of programming efficiently and ultimately saving time. Now, let's switch back to our part. I already have an existing SolidWorks coordinate system and will now go through the workflow of establishing my machine environment by selecting the appropriate type machine, the tool crib, the post processor, and finally assigning my fixture coordinate system. For my stock manager, I'm going to use the default bounding box profile and assign the SolidWorks coordinate system as well. To determine what type of machinable features are available, I'll run extract machinable features and pick and choose what I want when generating my toolpaths. Let's explore this rectangular pocket 1 strategy, as I want to change it to a rough finish edge break strategy. Once I select the green check mark, I now have this specific strategy assigned, and I'll generate my operation plan, then generate toolpath to see what I initially have. Now, let's see if I can make this rectangular pocket 1 operation more efficient. First off, since I want to use a different size tool, here's a cool trick. Switch over to the CAMWorks tools tree, and if you want to change tools quickly, simply drag this rough mill 1 and drop it on top of the end mill of choice. In this case, the 3/8 diameter flat end mill. Next, I'll make some minor changes to the rough mill 1 operation so that I'm using a 2.5 axis volume mill, well, just because we can, then update everything by selecting preview and ultimately the OK button. At this point, I'm happy with the current settings for contour mill 1, which finishes the vertical walls of this pocket, and contour mill 2, which creates an edge break on the top profile feature. Now here's the cool part. I want to take all this knowledge and apply it to this irregular slot 1 feature along with its different depth. Switch back over to the CAMWorks feature tree, right mouse button click on the feature strategy I want to save as an operation plan, and let's give it a meaningful name. Well, we'll call it test condition. After selecting the green check mark, the Create Feature Condition dialog box is now active. Editing numeric values of width and depth are available, and for this example, I'm going to increase the width value as well as specifying a larger depth. Now, I'd like to take this customized strategy and apply it to this irregular slot 1 feature. However, when I access the strategy type for this feature, I don't have access to my customized strategy. This is where Map Mill feature comes into play. So let's open up the CAMWorks TechDB one more time, Map Mill Features, and after locating ID number 11, Irregular Wrapped Slot, change the settings of the drop-down menu to a rectangular pocket. Save my changes, and then exit the TechDB. Back again to our model, let's edit the irregular slot strategy one more time. And you can see we now have access to our test condition strategy along with all the specific cutting tools. Using the same workflow as before, generate operation plan, then generate toolpath, we can now see graphically the same tools and toolpath as we had customized for that rectangular pocket. To clean up the CAMWorks operation tree, let's sort by operation type by simply clicking and dragging, then by the cutting tool itself. Select Apply, then OK to see how easy it is to sort and group the cutting tools for minimal tool changes. So, by creating a customized strategy, saving it back to the CAMWorks TechDB, then making it available globally by editing Map Mill feature gives us the opportunity to program efficiently by creating it one time, then applying it to other features for reuse. Now, I realize that this is a very simple part with two unique features, but what if we had something much more complex? Let's say, such as this mold base. Imagine creating strategies and operations for every single feature, or copying and pasting operations. Again, the key here is to work efficiently, which ultimately will save time in the long run. So, that's my top 10 time-saving features in CAMWorks 2020. It looks like I went over the 30 minutes, and I do appreciate all of you hanging in there. But these suggestions are just the tip of the iceberg, and really, I could spend the next several hours exploring more of what CAMWorks has to offer. Having said that, GoEngineer has decades of experience helping companies succeed using cutting-edge, industry-leading manufacturing tools. We are the experts with this technology and are passionate to help you leverage the power of CAMWorks and SolidWorks CAM for your machine shop or prototyping lab. If you would like to find out more information on CAMWorks, SolidWorks, or even what GoEngineer has to offer, feel free to contact me directly, and I encourage everyone to check out our free resources as well. This is Paul with GoEngineer. Thanks for watching.